Hello everyone and welcome back to a new session for Computer Science 2, MCS 2514, Summer 2022, Lawrence Tech. Today we are at week 2A. We're gonna go over chapter 7, chapter 8, and assign homework 2. I'm gonna go in brief over these chapters since I realized and noticed that you might be familiar with the topic. So we're gonna try to put both chapters, since they have a lot of info in them. We're gonna try to put all the topics in within one session. And if you have any questions, feel free to reach out. I have the book in front of me. So I'm on chapter 7, page 381. Starting with 7.1, arrays hold multiple values. So they are trying to define what is an array. An array is a container that stores and work with multiple values as long as they are of the same data type. You cannot have one container of different data types. So just like you declare an integer variable, my var, this holds or stores or carries only one value. I can create an array of integers. So my array, and this would be size, for example, 5. This variable stores only one value. This variable, which is an array, stores 5 values. All these 5 values are integer types. So if I open my paint, this is the memory under the hood. Let's increase it. So this is the memory, and I have slots. When I say integer, my variable, we're gonna go grab 4 bytes for the integer and assign it to that variable. That's only one value. On the other hand, with arrays, when I declare an array of 5 integers, the operating system is gonna go and assign 4 or 5 slots, 4 bytes each, and assign those memory addresses into my array. So my array is one variable, but it's gonna represent a block of memory, and it's continuous in memory. Means this block comes right before this block, right before the third block, right before the fourth block, etc. And the array as an array name will hold the memory address of the first item. So the name of the array, if I go ahead and display it, it's gonna display just the name. Notice only the name. If I display this, it's gonna display the beginning address of the memory. So my block of memory starts at this address. The next one is +4. The next one is +4. So next one would be 12. 12 is B. Remember with the hexadecimal, we have letters. So 9, then A, then B, actually C, 12. So, B. So if I go ahead and add 1, and we're gonna go over this later, when I use arithmetics with the name of the array, means go to the next slot in memory. Right now, this is what the name is. The name is representing or carrying the memory address, which ends in 8, 68, I think it was. So it was something 68. That's the name of the array. +1 arithmetics on the name of the array means go to the next block, not next slot. It's not next byte, it's next block. So this would be the next block, which is 4 bytes away from the first one. Why 4 bytes? Because every integer is 4 bytes in size. Similar fashion, +4, +4, +4. So if I go ahead and display it, Did it display? Here it is, C. So 9, A, B, C. Then if we, so it's E, C. Then if we want to add 4, it's D, E, F, then back to 0. So if I go ahead and tell it, go to the next, it's gonna be 8, 0. Now, that's the declaration, the way you declare an array, and the definition in general. And the book shows a lot of figures, how it's stored in memory, how data are stored in memory. If you don't understand my painting, so go refer to the book. You need to know that it just works like a regular variable. An array works exactly like any variable. It can store, except the fact that it can store a group of values. And as I mentioned, all of them should be of the same size. One thing to know, this size, the size of your array at compilation time, means before the computer is running. You cannot ask the user for the size of your array. This value needs to be literal, just like I have it right now. This 5 is literal. It's literally 5. It can't change. It's fixed, constant. So this value right here cannot be a variable. Means if I say int my variable equals 5 and then use my variable as a size, this is illegal. It's compiler is not gonna like it. It's gonna say, hey, you cannot, at compilation time, you cannot allocate variable memory. You cannot ask the user, hey, how much memory do you want? Oh, okay, you want 5, here you go. I allocated 5 integers for you. So no, at compilation time, this size needs to be a constant variable. As long as it's constant, then you are allowed to use it as a size. In case it is variable and not constant, you cannot use it as a size. So notice, since this is constant, I cannot ask the user enter the size. Since it's constant, I can't ask the user for a value because this is constant. You cannot use it on a const. See, you cannot use it on a constant. So the fact that this is const means I can use it as an array. With arrays, you cannot ask the user for the size. And that's the disadvantage of arrays. So there are a lot of advantages and there are disadvantages. So now let me show you how you can declare an array and initialize it with values. So right now I have it as an array that is allocated in memory, but it has no data in it yet. As a matter of fact, it has data which is garbage data, but it doesn't have a meaningful values, nothing in it yet, nothing that represents a meaningful, useful information for my program. Right now, at this point, it's garbage. If I go ahead and I hover my mouse on it, it's gonna show me first the address, the beginning address of this block of memory, 5 integers. Then every slot, every block, which is 4 slots, since an integer is 4 bytes. Every block has some garbage data. This is the default value of an integer. It's just random, not pretty random, but it's garbage, junk value. So I can right away declare and initialize it. And the way I initialize it is I say equals, open curly braces, for example, 120, 345. Now I gave it 5 values. So now it no longer at this line, when this line executes, it's not gonna store garbage values anymore. It's gonna go allocate memory for 5 integers and populate those 5 blocks with these values, respectively, 1, 20, 340, and 5. So if I run and I hover my mouse, I have the beginning address of this array and then the values. This is called, well, it's called initializing. And then there is partially initializing. Notice with the case when you partially initialize an array, this is legal. I told it to allocate memory for 5 integers, but I only gave it the first 3. The 2 following these 3 are no longer garbage. The moment I assign values, then it fills out the rest with zeros. So when I hover my mouse, I can see that they are zeroed out now. So it's going to use anything that I specify, then fill the rest with zeros. So this is how I assign values to my array. How do I display or how do I access, whether it's a get or set? How do I grab values from my array or set values to my array? And for that, I use the square bracket. Square bracket takes a subscript or an index or a position. So in this example, in this line, which value would I like to display? In this case, I would like to display the first value. We should know that the first item in an array or any container starts with the index 0. It's just how computer science is. Computers start from the location 0, meaning this address 68 is item 0. Then this is item 1, then this is item 2, item 3, item 4. So if I have an array of size 5, the last item would be at index 4, which is n minus 1, size minus 1. This will display the first item. This will display the second item. This will display the third item. 3, 4, 5. Notice the problem with arrays, another disadvantage is I can access out of the boundaries. Yes, I told the system to allocate memory for 5 integers. However, I'm accessing the 6th item. It's legal. Visual Studio as an IDE is pointing it out. It's telling me, hey, you're doing this and that, but it is legal and it will build and I will be able to access the memory. Notice 1, 20, 300, 00, some junk. The reason why this is some junk, because it's a free memory. It's some unallocated memory, some released memory, and it's ready for the operating system to grab. So the problem with arrays, it doesn't go, it doesn't, let me put it in a different word, it does allow out of boundaries. For example, if I put this for int I equals 0, let's say I want 1 million. And then I say I++. On each iteration, hey, program, I need you to display my array at index I. Remember when in our previous session, we mentioned that every time you open a file, you need to close the file. And the closing the file is as important as opening the file. Why? Because you want to release the file. You want other programs or other services or other processes or a new function call to use that file. You don't want to keep a lock on that file. Otherwise, it's not going to work and you're going to have all sorts of errors. In this case, I was earlier able to access the item number 6 because it was a free memory. But at some point, I'm gonna access a memory that is allocated for a different service and I'm not allowed, or my program is not allowed to access memory that is allocated for different program, and my system will crash. So that's the disadvantage of my array. The fact that it allows you or your program to go out of the bound produces a lot of hassle and headache and bugs. Notice the fact that it was allowed to go out of the boundary. At some point, I reached an address that I am violating the reading. I cannot access and read from that location. Notice it displayed a lot of, actually, let's give it a number. So let's say see out I plus 1 memory at memory at I plus 1 so at memory at this line, right? At this line, we have this. So let's see how much did we end up. Well, yeah, it didn't look nice because of my properties. Font 20, go. I'll do this more, a little bit. Properties, font 16, go. Still. Okay. Anyway, I'm just curious. It's part of me, but you don't have to go that deep, but you get the idea. The disadvantage of an array is it does allow going out of the bounds, and that introduces a lot of errors, whether it's logical or runtime. So how do I access elements? This is how I access elements, using the square bracket with a subscript, with an index, whether it's 0 for the first item or 4 based on the size minus 1. So size minus 1 is always the last item. So back to the book, 7.1, defining an array with the graphs and how it's stored in memory. Then 7.2, accessing array, inputting and outputting from an array, just like a variable. I can say I need at this location the value to be 1,000 or 10,000. So now I can display it and it's going to show me 10,000. So this is how I access and get or read values. And I show you how to initialize. I also showed you partial initializing. Then they mention implicit array sizing. So it's possible that you can declare a variable without a size as long as you initialize it right away. So I can remove these. I can remove these for you just so it's clear. When I say int my array without a size, that means it's the size of whatever I'm assigning it to. So now this, after this line gets executed, my array would have size of 3 items only. If I say 4, now it is partially initialized. The fourth item would be 0. If I say 2, it's going to say, hey, you can't do that. You're saying that you only want 2 integers, but you're assigning it 3, so that's illegal. Too many initializer values. The book mentions a topic at page 392 that says reading data from a file into an array. And following that, there is a next topic says writing the contents of an array to a file. At this point, you know how to read from a file. You know how to write to a file. You know how to store data in an array. You know how to read data from an array. So I'm not going to go over how to read data from a file into the array and then back writing data from an array to a file. You should know these by now. Then topic 7.3, it mentions, hey, watch out, no bounds checking in C++. Arrays do not do bound checking in C++, which is what we just demonstrated. An array allows you to go out of the bound, so watch out. Then the next topic is 7.4, the range-based loop. The range-based loop is just, remember when we explained about loops, we explained only 3 loops. We explained while loop, do while loop, and for loop. This type of loop, which is called range-based for loop, it's just a for loop, but it looks nicer. Anytime you don't need, anytime you have a container, whether it's an array or any other containers that you're gonna see in this class, you can use a range-based for loop as long as you don't care about what position every item is. So again, if you have a container and you just want to iterate it from beginning to the end and you don't care about the exact or explicit position for each value, then range-based for loop is nice to see. And the syntax is basically, let's say I have this, only 3 items. Let's say I have 10 items. The rest are 0. The range-based for loop goes like this. I say for int item, for example, item in my array. For each item, see out the item. So when this line executes, I only know, or the code will only know the value of item. It's not gonna know the position of item. So that's why I said, if you don't care about the position, then a range-based for loop looks simple and nice. I just want to iterate and display instead of doing for int I equals 0, I less than size, this and that. So here you go. It displays all of them from the beginning to the end, to the last item. Then we go to, oh, actually, I forgot to mention one thing about this for range loop. You see item at this point. Let's put this in a curly braces. I'm going to display it, right? And then I'm going to say increment it. Then I'm going to say display it again. Actually, we don't want to display it again here. I iterated, I incremented each item, and I broke out of the loop. Then I'm going to iterate it again and display it again. So notice the behavior is we're going to increment a copy of the value in the array. Notice once this is done, these are the original values. That means this item that we displayed here is a copy of what's stored in the array. I have 1 as the first item, 20, then 300, then zeros. When I increment, I'm not incrementing the value that is in those assigned or allocated memory. I'm incrementing a copy of it. This syntax gives me a copy of each item, and I can do whatever I want with it. Notice, I incremented, right? I displayed, and on each iteration, I incremented. Once I broke out of the loop, I iterated my array again, and it's still the same values. So whatever I incremented above was a copy of the value and not the value itself, not the value stored in the memory. It was a copy of it. Sorry, it was 1, 20, 300. However, I am allowed, or I can use it by reference. And that means give me the memory address of that item, and I want to use it and modify it and store it back in the memory. Here is like getting the actual reference, the actual value in the memory, not a copy of it. So notice now the different behavior. I iterated, I incremented on each iteration, but I incremented by reference. Now the original values has been modified. And the syntax is adding this ampersand before the item. So between the data type and the name you give it. Here I can give it whatever I want, whatever name I want, and it will work. This is a range-based for loop. Then we go to you know how to process array contents. That's topic 7.5. You know increment and decrement operators. You know arithmetics. So it's just telling you that you can use arithmetics. You can add and subtract two values together. Then there is a topic that says "Zoo shall not assign." What they try to say in this topic is, if I have two arrays, so my array 2, then this is 2. Let's say this is 1, 10, 100, 2, 20, 200 to differentiate. Then let's say, as a matter of fact, I don't want to give it this. Let's say I want my array 2 to be a copy of my array. What the book is trying to say is you cannot do that. Visual Studio is not going to allow you. Maybe other compilers are going to allow you, but Visual Studio is not going to allow you. And this is wrong. Why? Remember at the beginning of the session, we said my array is the memory address. It's not the value or all the values in that array. My array as is the beginning address. So here you're giving it as a memory address, you're giving it to the other array, and you cannot do that because the array itself is well, we don't want to introduce pointers right now, not yet. This is a constant pointer and you cannot change it. An array is a constant pointer. So an array is a constant pointer. You cannot assign it a memory address. So in order to copy an array to another array, you need to iterate, whether it's a range-based for loop or not. So I can say int, or I can say auto in C++. If I don't care, or I don't know, I just say auto. Each item in my array, I need my array 2 to be at sorry, in this case, I need a position at I less than 10, I plus plus. At this position of array 2, I need the value at that position. So now they behave as parallel arrays. At this position is equals to this position. At position 0 equals to position 0, 1 to position 1, 2 to position 2, etc. So this is how you copy an array to another array. Though shall not assign. Instead of assigning, this is how you do it. Oh, it's an array of size fixed. Now, if I go ahead and display my array, I'm gonna see that my array has the same, my array 2 has the same values as my array 1. So 1, 10, 100, and zeros. My array 2 is gonna have the same values. In the same fashion, if I have two arrays that have similar values, I cannot compare them for equality using their names. Although they have the same values in them, in the memory, my array is storing a group of values that are the same as the group in my array 2. However, these two are never equal. Why they are never equal? Because this is a memory address. When I initialized and declared this variable, the operating system allocated memory from the free memory that the operating system knows about and allocated it to my array. So the next time a compiler asks for memory, eventually it's not going to give it the memory from the previous line because those memory blocks has been assigned or allocated to this variable. So my array is carrying a memory address. My array 2 is carrying a different memory address. Even though the groups are right and same and equal, this will never be true. This cout impossible to happen. This is impossible to happen. We will always end in the else statement. Cout, of course. Even if we run this 50 million times, they are never equal. So in order to compare two arrays, if they are storing the same group, again we need to iterate. We need to iterate my array, and on each iteration we need to compare position 0 from this array to position 0 for that array, position 1 to position 1, position 2 to position 2, etc. Then the book speaks about passing arrays as function arguments. When I pass an array, or when you pass an array, you're passing it by the name, right? Let's say I have a function that says display array, and I give it my array, right? I gave it my array. Here it is. This is my array. I'm gonna say this doesn't have to return anything, and it's called display array, and it takes an int array, and that's it. Then I define it, and I say, hey, you see the prototype declared above? Here is the body for it. It takes an int a array, a for argument, and now I'm here, cout blah blah blah. When I receive this, I'm receiving the beginning address, right? When I receive the beginning address, this worker function, every function has a scope. So every function has access to whatever within the scope. Within this scope, I have the beginning address. So as a worker myself, let's say my mindset at this point is this. I am the worker function. I am a function that my responsibility is to display an array that I receive as an input. When I receive a beginning address, how do I know what's the size? There's no way I can tell what's the size. And the fact that an array allows out of the boundaries access, that means it's impossible to know the size unless the caller function or the boss function gives me the size. So the boss function or the caller function needs to display an array. It gives me the beginning address and it tells me, hey, this has 10 in it. Display only the first 10. The first 10 are what's assigned to me. So here, const int l size. Since it's const, we use capital case, capital letters. So size is 10. Then I replace size here, and this is the way you want to do it, because in this style, this coding standard, if I want to change the size, I only change it in one place. However, if I had it like before, like this, if I want to change the size, I need to go over all the lines of code and change them one by one. And imagine reading every line of code and checking, oh, does this need to change or not? No, you don't want to do that. What you want to do is something like this. You assign it once. As a matter of fact, you put it as a global variable. You put it as a global variable. This is the size, and everyone references it. If you want to change the size, or the requirement has changed, or someone asks you, your boss, your customer, to have a different size, then you change it in one place. So every time you need to pass an array, you need to pass the size with it. So the prototype has changed. Also, the definition needs to reflect the change. Now I'm good to go. As a worker function, I'm good to go. I have a where the memory block starts and how many I need to iterate. So now I can say, okay, for int I equals 0, I less than size, for each iteration display I. Yeah, or there is a logic based, actually business requirement based logic, and it's called Sentinel. Sentinel is having a value at the end that indicates the end of the data. For example, business requirement or business requirement based logic means it depends on your program. What is your program trying to do? Then you can hack it or trick it in a way that indicates the end. For example, let's say these are my grades. My grades have size of, I don't know, 100. I'm not gonna have a class, at least not in the near future. I'm not gonna have a class that has more than 100 students. So 100 is enough. Then I'm gonna say, okay, I declared an array, garbage array. Sorry, garbage array. Then I'm gonna ask the user. So while L input is not -1. -1 is my sentinel. My sentinel based on my logic. The fact that the logic says that there is no grade that is -1, or maybe no grade above 100, also above 100 could be used. The fact that the logic or the business says this array is my grade, that means there is no way I can have a negative. So I can use the negative as a way to indicate the end of the data. For example, int L sentinel equals -1. Also, this could be global and const. So I can change it in one place. But anyway, then I have a L input from the user that is equals to 0 for now because I want to trigger the while loop. So I'm gonna say enter next grade. Then cn into L input. Now that I entered into CL input, if L input is not -1, then L my well, as a matter of fact, I don't care. I want my input, whatever it is, to be in my array. So I use it, then increment it at input. Now that I have this, I need I equals to 0, and we pass it here. Now that I have a sentinel, I no longer need to pass the size for a walker. Why? Because I know the sentinel. So I remove these, and I remove these. Now in my display data, I can say for or while true, right? Infinitely. Keep going until a array at I is not equal sentinel. If that is the case, then display a array. Oh, I can't do that here because I need it. And L. Then I plus plus. Once you use it, do it. So here, int I equals 0. So I'm gonna start from 0 as long as the value that I'm on is not -1, display it and keep going. So if I run now, what's my grade? Oh, first student scored 60. Next student scored 77, 90, 60. I can keep going, right, with numbers. I can keep going up to 100. Once I'm done, and I know I'm not going to have more than 100. So once I'm done with all students, I can enter -1. Once I enter -1, this will break out. Then it's going to display all the arrays. So if I put my breakpoint here, and then I hit, now it's going to go on. So the fact that I'm in this scope between this scope, when I hover my mouse, I do not see all the values. This function or this worker function has only access to an address that arrived from the outside. A boss function or a caller function called me as a worker function, called me and gave me a beginning address. I don't know where the end is, but I know that it ends at -1 based on the business. So I can say go on, and it will display everything until 35, until it reached the sentinel. See, it displayed all of them all the way. Oh, the function found -1, then don't display and stop, break out of the loop. It's no longer, there is no more data in it. So this is the topic for functions as arguments. Then they go over a two-dimensional array. Two-dimensional arrays, in general, 2 dimensions is very important because everything you see on a screen is 2-dimension. Any image you see is stored as 2-dimensional container. An image, any image, flowers, any flower, see, any flower you want to display, this is stored in memory. Here it is, stored as 2-dimension. You have height and you have width, and on each height you have a row of pixels, and on each row you have columns of pixels. So this here is 0, 0, 0 rows, 0 columns. Then the next one to the right is row number 0, column number 1. Then the next one is row number 0, column number 2. So 2-dimensional array. There is a topic on it because we are running a little out of time, and I need to go a little quicker just because I noticed that you guys did homework 1 and project 1 very good. So this might be a little boring for you that I'm going into details. However, if you think I'm going too fast, stop me, stop me, reach out, ask questions. So I'm passing on 2-dimensional array. If you don't know 2-dimensional arrays, read the topic and then ask me questions. Then that also they go by arrays with 3 or more dimensional. So you have 2-dimensional arrays, you have 3-dimensional array in a 3D space, you have 3 dimensions, X, Y, Z, and you have more than 3 dimensions. You have containers of n dimensions. You never know. For example, in a factory warehouse, right, where let's say cases of juice are stacked on pallets, an array with 4 dimensions could be used to store bottle number or stack or pack of bottles for each pallet. So you have a warehouse, and that warehouse has aisles, and on each aisle you have like ground, then a shelf, then another shelf, then on each shelf you have palette of bottles, and that palette has one case, second case, third case. So how do you locate a case? You need an n dimension. Well, not an n, 1, 2, 3, 4 dimensions. That's 4 dimensions per warehouse. Now, if I have multiple warehouses, that's a 5th dimension. I need a container of 5 dimensions to represent all the bottles across all warehouses, right? You're going to have rows for which warehouse, a dimension for which warehouse, another dimension for which aisle, another dimension for which shelf, another dimension for which part of the shelf that piece is on. So moving on, then they introduce vector briefly. Vector fixed. So remember how I said arrays has a lot of disadvantages? So C++ introduced a new container that fixes all the disadvantage or provides a solution for all the disadvantages from arrays. They share a lot of common though. There are a lot of commons in between arrays and vectors. For example, the same way an array holds a sequence of values sequentially in memory, vectors also store values sequentially in memory. Also, a vector stores its elements in a same type. Similar to the array, you cannot store different data types in an array, similar to vectors are. You can only store no matter how many items you need, but all the items need to be from the same data type. Also common is to access values or items in a vector, you use the square bracket, just like an array. However, the new things in a vector, and the things that vector offers over arrays are you don't have to have a memory, you don't have to have a size on compilation time. You can declare a empty vector, and on runtime change the size, add items to the vector. I can initialize a vector at the beginning with size 10, and during the runtime, I can change it to 15. I can add up to 20. I can add up to 1,000. I can also reduce it from 1,000 to 500. And vector under the hood will maintain the continuity of memory. Means if I start my program with size, let's say 5, with size 5, and on runtime I added items, vector will maintain the continuity. It will go and ask the operating system and maintains it under the hood. If you need more details, let me know. So there are code on how to declare and how to use vector, but it's the exact same like an array. Right now, they introduce only few methods that are important. For example, a size vector provides you the size method. You can just call a method called size. Hey, vector, give me the size, and the vector will return the size of its elements, how many items in it. So remember the hassle we had about passing an array to a different function or declaring with a fixed size. You don't have all that with a vector. You can just pass the vector and call a function that gives you the size and then iterate based on the size. As well, you can assign vector to another vector. Also, you have methods, list of methods that are on page 448. These are the main methods in vector. You have at, which is square bracket, clear, empty, pop back, push back, resize, and swap. These are the most important functions. And there should be erase. I don't see erase. Erase will, so pop back will remove the last item. Push back will append a new item. Erase takes a position and erases the item at that position. This is it for chapter 7. Excuse me, I'm gonna take a break really quick. I'm gonna pause recording. Okay, I'm back and I'm about to start with chapter 8, searching and sorting arrays. We're searching and sorting algorithms as well, because this chapter speaks about algorithms. What is an algorithm? It's a set of specific instructions in a specific order that resolve or perform a specific task. In specific, search algorithms. What is a search algorithm? A search algorithm is a method to locate a specific item in a larger collection of data. And this section in the book discusses two algorithms for searching the content of an array. It discusses linear search and binary search. Linear search is simply sequential search. So if I have my array, let's say this is my array. It has some items. And I need to find a specific item. Let's say I'm looking for the item or the value 2 on my array. These are 1, 3, 6, 2, 4, 3, 8, 7, 5, 9. Linear search is simply also known as sequential search, uses a loop to sequentially iterate or step through the array, starting with the first item. So linear means straight line, like this, from the beginning to the end, linear, sequential. So it starts, I'm looking for the value number 2. I want to know where is value number 2, which position, which index. So the algorithm starts from the beginning. Hey, item number 1, the first item, are you number 2? No. Okay, go to the next item. Hey, are you number 2? No. Okay, go to the next item. Are you number 2? No. Okay, go to the next item. Are you number 2? Yes. Okay, then report 3, which is the position. I found the value number 3 linearly. Sorry, I found the value number 2 linearly or sequentially, and I found it on position number 3. So this is simply put, this is a linear search. Anytime you iterate from the beginning till the end in a sequential fashion, in a continuous fashion, in a linear fashion, that's a sequential or a linear search. Of course, once you find the position or find the item you're looking for or the algorithm is looking for, you don't need to continue. So the maximum number of comparisons that you could do is n, whatever the size. In case the value you're looking for is in the last position, then you're gonna do n comparisons, all the size. That's the worst case scenario. The best case scenario is having the item you're looking for at the very beginning. Then your algorithm has to do only one comparison. In case it's somewhere in the middle, then it's gonna find n log n or less than n not times of comparisons, find the item, the specific item we're looking for, and then break. It doesn't need to continue. So worst case scenario is n comparisons. Best case scenario is one comparison, and then the rest is log n. So you're gonna have a loop, something like this. Let's say I have I have an array. My array equals 1, 2. Or what did we have here? 1, 3, 6, 2, 4, 3, 8, 7, 5, 9. And then the target, my target, the specific item I'm looking for the item number 2. Let's say, so 2, 4, 6, 8, 10. So this is 10. Then I have a function, for example, called linear search. This method takes an array, takes the size of the array, and takes the target we are looking for. So this method returns the position. Where did we find? Where is the target located? So cout display the position. Now, prototype, this returns a position. The position is an int. There is no decimal in the position. So the return type is a integer. The name is this. It takes an array of integers. It takes another integer for the size, and it takes a third integer for the target. Then I go and define it. I say, here is the return type. Here is the return type. Linear search, it takes int a array, int a size, int a target. In my case, I can start by saying, okay, I'm starting from result or position, we can call it. I'm starting from -1. right? If it's not found, I'm gonna return -1, means it's not found. If I start from 0 and I don't find the item, then I'm gonna have to return 0, which can be confusing. Hey, is 0 means, does 0 mean found, or found on position number 0, or found, or not found at all? So I'm gonna start by saying it's -1. In case I find it, I set the value to result. In case I don't find it, then I just return result. So L result. Here I'm gonna try, in this, between these two lines, I'm gonna try to find it. If I find it, then I'm gonna invoke result. I'm gonna change the value of result. In case I don't find it, I do nothing, then result will be returned as -1. Then I'm gonna have um, a way to keep track of my index. So I'm gonna call it index I. You can call it I. So L index. I'm gonna keep it started from 1. Then I'm gonna say it's not found. Bool. So I'm starting by saying not found, right? The same initialization logic I'm gonna use for this Boolean. My initialization is pessimistic, not found, and the result is -1, so false. Now I attempt to find. In case I find it, then I say, okay, found is true, and result is whatever the result is. So I'm gonna say, while, what are my cases? While I still, if I bring back, in case I wanna go linearly and find that item, what are my cases? My break conditions would be, I either reach the end, no more data, or I found what I'm looking for. In other words, if I'm starting from here and iterating, in what conditions do I stop? There are only two conditions. I either found the item, then I stop, or I'm looking for the item and I reach the end. So I have the size, right? Meaning, while my index is less than size, while this is the condition and it's not found yet. If this condition is true, if I am still within the size, but I found it, I still need to break. So both these conditions need to be true in order to break. I need to, I didn't find it yet, and there are still more to go. So while, if this confuses you, we can do it like this. While found is false, and while index is size is less than size, keep going. While I'm going, I'm gonna check, I'm gonna do the comparison. If a array at my index, at the position I'm on, is the target I'm looking for, if that's the case, then set result. So set result is at this index, L index. And found is true. This way I break out of the loop. Done, found. Oh, and in case this is not the target, so if this is the target, do these, and found will break out of the loop. If this is not the case, then I'm gonna say just move to the next one. Move to the next one. In case I didn't find it, and this is the last index, then this will fail. Then the entire statement will evaluate to false, and it will break out. It will return result. So I'm looking for 2. 2 is in 0, 1, 2, 3. Then this line should return 3. Here it is, 3. If we want to step through the code, stepping into a array is some data. Memory address starts from here. and the first item is 1. I cannot see the rest of it because at this point, it's just treated as one beginning address. The compiler in this scope doesn't know the end, but in this scope knows the end because it was declared right here. So I have a beginning address, I have a size, and I'm looking for 2. Okay, starting from not found, the mentality of not found. Index is beginning, mentality is not found. While this is true and this is true, both need to be true in order to enter. Is index less than size? Yes, index is 0 and size is 10. Did we find it yet? No, we didn't find it. Okay, so both of them is true. Enter. Hey, at this index, at 0, is this our target? No, it's the number 1. Okay, then move. Is this the target now? No. Okay, then move. Is this target now? No, then move. So now it is the target. Hey, at this target, at this position, is this the target? Yes. Okay, cool. Then this is where we found it. We found it at index number 3. And we trigger breaking out of the loop. Hey, found, you're now true. Okay, move to next. Hey, did we find it? Yes. Okay, this will evaluate to false. This is still true, but false and true, the entire statement will evaluate to false. Remember with the logical and, both of them need to be true. Return result 3, display result, boom. So that was linear search. Linear search is inefficient. But what's good about linear search is it's straightforward. I look in the code, I understand right away what it's doing. It's clear, it's simple. You know, it's the simplest method that you could do for searching for an item. One by one, right? You go from the beginning to the end. Hey, are you what I'm looking for? No. Okay, are you, are you, are you, are you? So it's very simple, but it's inefficient. It's inefficient because of the different scenarios that you have. If you have right now, we have a simple example, 10 items. But what if you have a million item? Imagine you have a million item, and every time you need to find a specific item, then you have to iterate. You have to iterate 1 million item, right? Because the average is having the item in the middle at 500,000 and position 500,000. So that's the average. Every time you're trying to search for an item, the average is 500,000 comparisons. So it's inefficient. The book tries to say that in this section, and then it introduces a new search, which is binary search. So it's a linear search. Is the advantage of the linear search is its simplicity. It's very easy to understand and implement. Furthermore, it doesn't require the data in the array to be stored in any particular order. So the order doesn't matter. Whatever the order is, I can start linear searching. However, the disadvantage is it's inefficient. If an array If the array being searched contains 20,000 items, the algorithm will have to look at all 20,000 elements in order to find a value stored in the last element. So if what I'm looking for is 9, I have to iterate number of size times. Whatever the size is, iterations equals to iterations. Then it introduces binary search. So binary search is an algorithm. It's a smarter algorithm, kinda. It's a clever algorithm that is much more efficient than a linear search. The only requirement for a binary search is to have the data sorted. The data must be sorted before starting binary search. It's called binary because by two. Linear search starts from the beginning all the way to the end. Binary search starts from the middle. Starts from the middle, and the fact that values would be sorted for example, 1, 2, 3, 4. We had 6, now 7, 8. We no longer need 7, we need 9, and we had maybe 2 sevens. So 7, 8, 9, 2, 4, 6, 8, 10. So let's say two threes, 6, 6, 7, 7, 8, 9. So if they are sorted, I start from the middle. What is my target that I'm trying to find? 2. I start in the middle. Hey, is 2 less than 6 or greater than 6? The fact that the array is sorted and the fact that 2 is less than 6, I immediately eliminated half of the data right away. Boom. I no longer need to look right because I know that my target is less than 6. So now that I eliminated half, then my focus would be on these items. I also repeat, I look in the at the middle. Hey, is 2 less than you? Hey, item in the middle, is my target less than you? Yes, it is less. Okay, then I eliminated half of my data. Then again, to the middle. Hey, 1, is it greater than? Usually when you are even and you go to the middle, you grab the left one. So hey, 1, is my target greater than or less than? Well, it's greater than. Okay, then move away from me. I don't need to look to the left portion, at the left portion. Come on. I just need this. Yep. Since I no longer have a middle and the size is 1, then I found it. This is the position. So it only took me 2 comparisons out of 10 items. I only did 2 comparisons in order to find my item. However, in case of the linear earlier, when the data wasn't in a particular order, it took me 4 comparisons to find 2. So binary search, although it requires data to be sorted, but it's very efficient in this way. It eliminates half of the data right away. If you want to see an example, so let's call this binary search. And this binary search will take an array size and the target same, and it will return the position. Yep. So function blah. I know. Blah blah blah. Go here. Go here. Get back. Get back. Get back. So here is my array. It's sorted, and I'm looking for 6. 6 is at 0, 1, 2, 3, 4. So now I go to my focus. I'm a worker function now. Same case, I'm gonna say I need a position, which is like the result, L result. Being pessimistic, I didn't find it. I also need the bool, L found. I didn't find it. Starting from not finding it, returning result. So if the task in between fails, I'm returning -1, means it's not found. Then we need our boundaries. Remember how we start in the middle? How did I know this is the middle? Because I had boundaries. The very first time I started, my boundaries were, sorry, check. Okay. Sorry, back. So how did I know the middle? I knew the middle because the fact that I had boundaries. At the beginning, my boundaries were 0 and n minus 1. Is that right? The first item is at 0 and n minus 1, which is size -1, is the last item. So that was my boundaries. So I have an int called first item, and first item is at 0. at the beginning. Then I have last item, and last item is at index a size -1. Then I'm gonna do similar loop while it's not found yet, and while first is less than or equal last. So while I still have a group of data, once first becomes above last, I should stop. There is no way, there is no point of continuing, because you're gonna see that first and found, first and last will be modified throughout this. The boundaries are gonna change every time I splice or slice uh, half of the data. Last will move to the left, and first, in case I eliminate left section, then first is gonna move to the right. So as long as first and last are in this condition, first is before last, because if in case I have first and then last has been moved to the left of first, then I should stop. This was the end of the data. So while these are my cases, I'm gonna say, okay, the middle position. What is the middle position? Let's create a middle. Right now, middle is, I can start it here by saying it is L first. So it is it's a size -1 over 2. So I can say it is L first plus L second, if I want to be systematic. L first plus L second over 2. Yeah, yep. L last, sorry. Boom. This is middle. As a matter of fact, I could have just declared it here and then initialized it, not initialize it, set its value on each iteration. On each iteration, this is my middle. So on each iteration, every time I enter this loop, my middle would be the middle of the boundaries. Then I'm gonna say, okay, if my array, a array, at this position is the value, is what I'm looking for, a target, then I found it, right? Anytime it's equal to the target, then I found it. So L found equals true, then L result is whatever middle is. If this is the position we found it on, then this is it. And the fact that I invoked this variable, then the while loop is gonna break. I don't need to break. I don't need to explicitly say break. So if that's not the case, then I wanna check, is my target left of middle or right of middle? So if a array at middle is greater than target, a target argument. If this is the case, then move last, eliminate all the left section, right? Let's say this is middle. What's a good, yeah, this. Let's say I'm here. Then I'm checking. It's, well, sorry, it should be sorted, but you get the idea. So I'm checking. Hey, are you what I'm looking for? Oh, you're not what I'm looking for. Okay, is my target 2, the one I'm looking for 2, are you greater or less than 2? Then it's gonna say, in case it said it's greater than, then I wanna eliminate all the left section. So if this is if this was first and this was last, and what I'm looking for is less than this, then I move last all the way here. Then this would be my new boundary. You see? So I'm gonna say L last is equal to middle minus 1. I don't want middle because I already checked middle. I just checked middle when I did this. So I don't need to check it again. Just skip it. So skip middle and everything to the right. Yep. And the opposite case is if A array at this position, we are still dealing with this position. On each iteration, we are dealing with this position. Hey, is it equal? Is it greater? Is it less than? So is it less than target? If it is less than target, then move first. L first equals L middle plus 1, right? Here I eliminated all the right section. Here I'm eliminating the left section, means everything right to the middle. So plus 1. Save, return. Yep, so I'm done. Let me see out. So see out binary search, give it L array, L my array, give it 10 because that's the size, and give it my target. And it will display what are we looking for? 6, and it will display 0, 1, 2, 3, 4. Here you go, found it. And it found it in 3 comparisons, in 2 actually comparisons, better than linear search. So this is very fast, we agree. This has less steps than linear search in order to approach the solution, but it needs a requirement, and the requirement is it has to be sorted. The fact that it needs to be sorted, then the book introduces sorting algorithms. Sorting algorithms are very important, and there is no best sorting algorithm. We can't say that the best algorithm is this algorithm, because it all depends on the situation. In some situations, some algorithms, sorting algorithms, are better than others. In different situations, different scenarios, different use cases, different or other algorithms are better. I always liked this video when I was a student. There was this uh, visualize sorting algorithms. I don't know if you're gonna hear the sound. I don't know if Zoom needs me to allow it, but I don't know if you hear it. But if you don't hear it, just look up this, and it's gonna show you how different algorithms perform the task, and how different algorithms are faster than other algorithms. I don't know if you hear it, but every sound every tone you hear is a comparison, whether it's in the beginning, so different tones, right? Then it's starting from lower tones to higher tone. This would be the lower tone, this would be higher tone, to give you a sound effect on the way the algorithm is working. And the colors will indicate the number of comparisons. Then here, if you can see it, it says selection sort. And by the end, when it sorts all the data, imagine these are numbers, random data. So this would be, for example, the shortest one would be 1, the next one would be 2, 3, 4, 5, 6, all the way maybe 200. It depends how many spikes. So by the end, when this is done, it tells you it did 7, 8, 7, 5 comparisons. 15,500 array accesses, and 7.9 delay millisecond. So they reduced it, I guess, with some milliseconds to for us to see it. Maybe I can change the speed, but you can do it yourself. So I'm gonna play some just so you can see how different algorithms just behave different. So for example, selection sort. Selection sort, if I slow it down, selection sort, let's say starting from this case, selection sort takes this value, let's say this value is 10, and then knows that 10 exists here. There is an index that keep track where is the green right now. We are here. Everything to the left is sorted. We are here. Let's say this index is 10. So it keeps track of 10. However, while it keeps track, it iterates the rest of the data trying to find closest to 10. Then once it finds the closest to 10, it swaps it with the following item. So now it's 10, 11, and green then moves, we are now at 11. Then a new loop starts over. Okay, I'm at 11, I'm looking for 12. Once I find the 12, I swap 12. So that's why it's called select. I select the closest and put it in its place. Then I iterate again, select the best one and put it in back in place. Notice when notice the how did I say different algorithms are better in different situations. Notice with selection sort, the shorter the data or the smaller the data set is, the faster it is. Selection sort is very bad, well, worse than other algorithms on a large data set. Notice from the sound effect how it becomes very fast at the end. Once the data set is small, it becomes very fast. See how fast it was at the end? So it's good on small. This is insertion sort. Insertion sort basically starts from left, well, most of them, or all of them linearly start uh, from left to right. Insertion iterates the entire data set, it grabs the lowest if we are sorting ascending. So it iterates all the data set, first iteration, which one is the minimum, finds the minimum, and then it inserts it to the left. Now that we have the first item, we go to the next item and iterate again, find the minimum, and then insert it. Then the third position. So it starts inserting value into positions uh, 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 repeatedly, I can say, or continuously. So here, notice again, when the data is bigger the data, the slower it becomes. Look how slow now. It grabs the value and tries to find the best spot. Oh, actually, yeah, insert. So it grabs the following. Yeah, true. So if with insertion sort again, sorry, my bad. Let's say we are here. It grabs green, or we are in green. It grabs this and takes it, insert it in the right position. Then it takes the next one, goes, insert it in the right position. Then takes the next one, insert it in the right position. This is how many comparison it's doing. Insertion sort. This is quick sort. It's called a quick sort. And look how it starts from first and moves to the middle. And it does this multiple times, multiple iteration, not just once. So it does it, then it does it again, then again, until everything is sorted out. See how fast it is for large data? And you can tell it follows divide and conquer, which is similar to binary search. It divides the data to sections and takes the middle and moves from right to the middle, from left to the middle. Once this is figured out, let's say, not sorted, it doesn't sort right away. Once this section is figured out, kind of reordered, it goes to the next section. See how it always breaks in the middle and then moves from left to right. Merge sort. Merge sort will sort them in pieces, also like a divide and conquer approach. It divides them, sorts them in pieces, then merges the parts. Merge sort, here it is. This uses a lot of memory because it copies the data to a different array. You know why it's copying, it's sorting, then back to the array. Notice, for example, now while it's going from from left to right, it's copying these values to a new array. So it's copying to a new array in a sorted order, right? And then it dumps them back. It puts them back in this array in a sorted behavior. So you can do this heap sort. Heap sort is very fast. So you can play with this as much as you want. Another one I need to show you is different when a data set is already ordered. You know, if a data set is partially sorted, also data size. Some algorithms are very fast on large data set and very slow in a small data set. The way they approach it creates more headache or more steps than needed. For example, for an array that is 5 items or 10 or 100 or even 1 million. In today's world, computers are fast. 1 million is still maybe less. It depends 1 million what. Let's say you are on Amazon. You might be saying right now, oh, well, what I'm looking at, this is very boring. But you will be surprised how important sorting algorithms are. For example, I go to Google and I say bicycle, right? Bicycle, 1, 2, 3, boom. How much did this take? 1 second or less than 1 second. About 1,080,000,000 results in less than 0.65 seconds. Not just that, Google didn't just grab 1 billion result and dump it in front of me. It also dumped it sorted by, if I start from the actual data, not the advertisements, this data is sorted by relevance, sorted by most related first, most relevant first, then less relevant, all the way to the last page. Then the last page would be the least relevant. Imagine you are on Amazon or eBay, and then I say, okay, I want bicycle. Now it's sorted as well by relevance. The first item is the most related to my search criteria. However, I can sort, and look how fast it is. I can sort by price from low to high. Boom. In less than a second, it sorted all the results up to 20 pages, maybe more. I can sort it again, sort it again. So so there is an algorithm that is sorting based on a criteria, and it has to do it very fast. Otherwise, customers wouldn't like Amazon, and it would say, "Oh, our the website is so slow." So algorithms, sorting algorithms in particular, are very important, and it depends on the data set. It depends on whether it's partially sorted or not. For example, also you see this low to high, high to low. If the user is on low to high and then switches to high to low, there is a specific sorting algorithm that is so fast in swapping the order, while other algorithms might be very slow in swapping the order. So the fact that we started from a sorted array, it's wise to pick a specific algorithm. So it depends, how are you starting? Are you starting with a sorted array? Are you starting with a partially sorted array? Are you starting with a million item, 10 items? So it depends on the situation. You pick the right algorithm. For this class, you're only responsible to know two sorting algorithms. One is bubble sort and one is selection sort. So I might ask you in the test, write a sorting algorithm or sort this array. You can pick whatever you want, bubble sort or selection sort. These are the two that you're responsible of. So back to the book. After binary search, they have explanation on why binary search is efficient. Then they have a program and the case study focused on software engineering. Excuse me, I need more water. Then we start with sorting algorithms. Sorting algorithms. And it starts explaining that many programming tasks require the data in an array to be sorted. Customer lists, for example, are commonly sorted in alphabetical order. Yep. Student grades might be sorted from highest to lowest. Product codes, etc., etc. To sort the data in an array, the programmer must use an appropriate sorting algorithm. A sorting algorithm is a technique for stepping through an array or a container and rearrange its content in some order. In some order, they didn't say ascending or descending, in some order, because it's based on the criteria: price or average customer review, etc., or feature, etc., etc. So some order. The result is in some order, particular to the business. Then they start with bubble sort. The bubble sort is an easy way to arrange data in ascending or descending order. It's called the bubble sort algorithm because as it makes passes through and compares the elements of the array, certain values bubble toward the end of the array with each pass. So bubble sort basically starts from here to here. It compares, hey, which one is bigger? The bigger goes to the right, the lower goes to the left. Then it compares these two. Which one is bigger? Come with me. Which one is bigger? Come with me. Which one is bigger? Come with me. Which one is bigger? Come with me until it reaches the end. On the first iteration, it's n comparisons. On the second iteration, it's n minus 1. On the third iteration, it's n minus 2, because we no longer need to go up to n. We already put 9 in place. We already put 8 in place. Sorry, this is already sorted, but I'm trying to visualize it for you. I can do a Google one, or you can do it yourself. Say visualize bubble sort. So it's called bubble because on each iteration, the larger bubbles into the end. If I'm doing it in descending order, if I want to sort in descending order, then the lowest bubbles to the end. See the difference? If it's in ascending order, the larger bubbles to the end. If descending order, if I want to sort in descending order, then the lowest bubbles to the end. So it's bubbling anyway. Bubble sort. There is a complete code for how to do the bubble sort and explain exactly how it does it in figures, but I prefer visualizing a video. If you are like me, you don't like that. So visualize bubble sort. Bubble sort. Here's bubble sort. See how when it started, it's comparing each two, and then the larger moves on. The larger moves to the end. The larger moves to the end. So this is bubble sort, ascending order. Then what else we have in the book? Of course, we have selection sort. Where is selection sort? So selection sort, my friends, selection sort keeps track uh, of the index on each iteration. It's similar to a bubble sort, but on each iteration, it keeps track of the index. And instead of swapping every two together, it just swaps it with the end, with the last item. You see here, back to this. If I slow it down, notice in bubble sort, now, let's do the end, boom. Notice with bubble sort, it grabs an item, right? And then it compares these two. Then it compares these two. So it keeps swapping every item. However, with selection sort, it doesn't swap, it just compares and then swaps by the end. Instead of swapping throughout the iteration, it just swaps with the end. So it picks the larger, it keeps track of the larger, it doesn't swap. So the large stays in its place. It keeps track. Oh, okay, the largest so far is here. Let me compare without swapping. Let me compare. Oh, which one is the largest? This one's the largest. Okay, so now this is the largest. I keep track. Instead of swapping, I keep track. Then I compare with the next one. This is small one with this one. Which one is larger? I'm still the larger. Okay, stay larger. Hey, which one is the larger? You're the larger. Okay, so now I keep track of this. Uh, I'm trying to draw an arrow. I'll keep track of this. So it keeps a track of the largest instead of swapping the largest. Bubble sort swaps. Swaps. You see how the large is moving? The large is moving until it reaches the end. Selection sort, nothing moves until the end. Once we reach the end, we kept a track of the largest. We swap this item here with the largest, and then we repeat. There are figures and there are codes. Let's see what else we have in the book before we call it for the day. Yeah, this is it, done. Review questions and exercises. So let me know if you have any questions, and good luck.